results that I'll show. Okay, so all of the numerical work that I'm going to show you in the second half of the talk, that's been done by Johannes, who's an amazing postdoc at Weizmann, and this work is done in collaboration with my long-term collaborator, Eris Berg, and also Steve Kivelson. And the data, a lot of the data that I'm going to show you, it's been possible to do all this work thanks to generous support from the NSF Exceed program. Okay, so the preamble to this talk is that superconductivity in the limit of flat bands is a highly non-trivial problem. Okay, and as I go along, I'll tell you why that is the case. So now, actually, before I continue, Cyprian told me that there will be lots of grad students in this talk, so please just interrupt me at any point of time and ask me questions. I have tried to make the first half of the talk very pedagogical. So usually when we think about superconductivity, there are at least two different challenges that we have to deal with. So first, you are dealing with electrons. Naturally speaking, electrons like to repel each other. So a question that we always have to grapple with is, how do you actually generate effective attraction between electrons? Okay, so that's only part of the problem. And once you have some sort of an effective attraction between these electrons, you ask, okay, I have some kind of a metallic state. How do the electrons actually pair up? Okay, so it turns out that even if you assume that there is some kind of attraction that's already present in this flat band limit, the problem is already very complicated. Okay, so in the rest of this talk, I'm just going to assume that there is some microscopic attraction that is present between the electrons and study the effect of that on the actual pairing instability, or at least address even if such a instability is even possible in the first place when the bands are just flat. Okay, and so that's the question we are going to address. Now, the problem itself has been stated for a really long time, going back to early work by Wolovic and others. For a long time, it was thought this is really mostly of academic interest, but of course that is no longer the case because, as I'm sure everyone here knows, thanks to the discovery of these moiré materials, there's really been a lot of work, including work done at Caltech in Stefan's group, which finds superconductivity, or at least very good hints of superconductivity across multiple moiré materials. And as I will discuss later on in the talk, in order to understand this, one really has to understand how you can generate superconductivity in the limit of a flat band. At least that's one limit from which one can try to start solving the problem. Now, actually, in the remaining talk, I'm not going to specifically study models that are relevant for, twisted bilayer graphene or any other moiré compound. I'm going to take a step back and write down simpler models which have a lot less complexity that we would ideally want to include for describing any of these compounds, and just go back to some basic theoretical questions. But as I will try to argue, even studying this problem leads to many new insights that will be useful when we eventually try to solve the full problem. Okay, so I want to start with very basic things. So this is what I call superconductivity 101, something that I assume a lot of you who have taken graduate level solid state physics have already seen. Okay, and to make things concrete, let's start with a very well-studied and almost paradigmatic model. So what I've written down for you here is some kind of a Hubbard model. We can write it, let's say, on the two-dimensional square lattice, where the electrons hop around on the sides of the square lattice. There's a conserved density of electrons, which I can change by coupling to an external chemical potential. And then just by hand, I write down an on-site attractive U interaction. Okay, so usually, of course, for many strongly correlated things, we write down the repulsive U Hubbard model, but here I just want to write down the attractive U Hubbard model. And so this is what I meant when I said I'm going to assume that there is some tendency for the electrons to just attract each other and try to form pairs. Okay, and that's what this means here. Now, if I want to solve this problem, the problem can be solved reliably within BCS mean field theory, which is fundamentally a theory of weak coupling. Okay, so when the strength of this attractive interaction is much, much smaller than the electronic bandwidth, which is set by these hopping parameters, you can really solve this problem at any arbitrary density. And this is what we usually do. And so the mean field transition temperature that one finds is given by some microscopic energy scale times this very famous factor of exponential of this dimensionless combination. So nu here is the density of states, and u is the strength of attractive interactions. And typically, the density of scales goes as 1 over the bandwidth. Okay. Now, the question is whether I can crank up this mean field transition temperature simply by either making my bandwidth smaller and smaller, which enhances the density of states, or equivalently just cranking up the strength of interactions relative to the electron bandwidth. Okay, if I do that, if I just literally take this expression for granted, then it would seem that yes, I can just arbitrarily crank up my mean field transition temperature. Now the question is, should we be doing that? And the answer is no, because this is a very dangerous thing to do. We should really stop and pause for a second and think about what it is that we're trying to do. Because as I said, this is a classic example of trying to extend or apply a theory far beyond its regime of validity, okay? So you start out by solving this problem in the limit where interactions are much, much smaller than the bandwidth. So I can't just naively apply the same theory and infer that I can crank up TC by going to the other extreme, by going to this particular limit. Okay, and the fundamental question that we should ask is, it's far from being clear that when I crank up the strength of interactions, I can immediately even infer that I will continue to have a superconducting ground state. And the bigger problem is that the normal state, meaning the metallic state out of which superconductivity can possibly arise, need not be conventional in any sense. So by that I mean, when we apply BCS mean field theory, we typically start out with a metallic state that has long-lived and well-defined quasi-particles, and then we introduce attraction between these quasi-particles and study the Cooper instability. Okay, and in this extremely non-perturbative regime where I have literally just one scale in the problem, the strength of attraction, it's far from being clear what the normal state will be like. Okay, so one needs to critically examine this problem. Now, it turns out, even for this paradigmatic model, I can actually solve this exactly using a numerical technique. Okay, and that's been done a while back. So the numerical technique is known as determinantal quantum Monte Carlo. The details are not so important, but it basically turns out if you write down the path integral for this model, it's possible to really just solve it exactly, compute all of its equal time correlation functions and so on, because this model with an attractive U does not have this infamous fermion sign problem. Okay, and so this has been done, and this is what the phase diagram looks like. So you can crank up the strength of interactions relative to the bandwidth. And indeed, when the interaction strength is weak compared to T, you have a superconducting instability at a finite temperature, and you can see how this sort of asymptotically approaches the mean field transition temperature. Okay, but then you start cranking this up, and for a while TC increases, but then roughly when the interaction becomes comparable to the bandwidth, so the bandwidth is 8 times T, you start seeing that you have hit a maximum, and beyond that, TC starts decreasing. Okay, and so the question is, why is that? Okay, now you might ask, what's really happening here? And one way to address that is to actually go above this temperature scale and ask what's happening to this normal state or the metallic state above TC. Okay, so one way to diagnose what's going on with that parent state out of which superconductivity emerges here is to look at its spin susceptibility. So the correlation function of its, let's say, SZ, okay, equal time. And I'm going to talk about that a lot more later on. But basically what you find is that at some characteristic temperature scale T star, which roughly scales linearly with the strength of attractive interaction, you start seeing a strong suppression in the spin susceptibility, okay? And what that means is that there is something that's favoring the formation of spin singlets, which is why the overall susceptibility is going down. But if you ask what the superconducting transition temperature is, there is no superconductivity. So the question is, why is that? Okay. And to understand that, one has to go slightly beyond what is covered perhaps in the first course in solid state physics.
Sorry, in the previous slide, can you tell what is the dashed curve on the right-hand side of the first plot?
Sorry, you mean this curve?
No, the first plot. This curve. This one.
I'm going to explain what that is in a second.
Okay, thank you.
Right. So as I said, in order to understand what's going on at very strong interactions, one has to go back and think about how you get superconductivity in the first place. So superconductivity is, it's a complex object. It's a complex order parameter that I can express in terms of its amplitude and its phase. Okay. And in order to get superconductivity, I have to ensure that both there is a finite amplitude for this order, and also that the phase, across your system, that's not just randomly scrambled. There has to be a notion of a phase order as well. Okay. And in general, there are two different energy scales in the problem that determine the pairing scale, meaning the scale at which the amplitude orders, and the phase ordering scale, meaning the scale at which all the phases lock up together. Okay. And then TC is basically determined by whichever is the lower scale in the problem. Now, in BCS theory, as I presented it, and as I'm sure most people have seen, when we talk about a mean field transition temperature, it's really addressing the question of the temperature at which the amplitude develops an expectation value. Okay. So let's now talk about what this other ordering scale is. So if we specifically focus on the case of 2 dimensions, the phase ordering scale is set by this object, which is known as the superfluid stiffness. And this is actually, so it has the same dimensions as energy. And this basically gives us a feel for how susceptible a superconductor is to phase fluctuations of the superconducting order parameter. Meaning, if I were to write down the free energy associated with the superconductor, it's the coefficient of this gradient theta terms. Okay. And this is something that is directly measurable, because turns out when superconductor exhibits Meissner effect. So let's just think about a 3D superconductor for a second. Then this ds is exactly related to London's penetration depth, which is responsible for Meissner effect. So one can measure this quantity in the lab in principle. Okay. Now, as I said, when we are thinking about BCS mean field theory, TC is really determined by the scale of the amplitude ordering. And if you actually go ahead and calculate the phase ordering scale, okay, this is typically much, much higher than the scale at which the amplitude orders. In fact, if you were to calculate this quantity for the 2D electron gas with the parabolic dispersion at 0 temperature, this is basically given by the Fermi energy. So the picture is at weak coupling, where all kinds of fluctuation effects are basically irrelevant, the amplitude develops an expectation value and the phase sort of orders immediately. It's not the rate limiting step. Okay. But that need not always be the case. So in fact, if I were to go back and think about what's going on here, turns out in this regime, what's limiting TC is really the phase ordering scale. Okay. And so how do we think about that? Well, it turns out for this problem, in this extreme regime of a large U over T, I can just start from the strong coupling limit. Okay, so I can switch off my hoppings altogether. First, just try to solve this problem. Okay, and this immediately tells me that because of this explicit local interaction, my system likes to form pairs, spin singlets, which I also told you there's direct evidence for from the measurements of spin susceptibility. And then we can imagine turning on a small hopping. Okay. And so that's the picture. You have these Cooper pairs that have formed locally. There's no phase coherence. But as soon as you turn on a hopping, you can do second order perturbation theory, and you can immediately see that these Cooper pairs can now hop with an energy scale that is given by T squared over, again, this is the magnitude of U. And it's precisely this scale that sets the kinetic energy associated with the Cooper pairs. And that is what this asymptote describes. Okay, so the picture is at strong coupling. You're not really breaking the Cooper pairs, but you're destroying the phase coordinates, and it's then limited by that scale. And in general, this is something that shows up quite often. So when we are trying to crank up superconducting TC, we might focus on trying to optimize one of these energy scales, but typically what that often does is that it comes at the expense of the other. So just like here, if you just try to crank up U, yes, you increase the tendency for formation of these Cooper pairs, but you destroy their phase coordinates, okay? And for this particular problem, I mean, this is almost a pathological limit. If you turn on the hopping completely, so set the bandwidth to 0, the system sort of decouples into a bunch of sites. And of course, there's no TC because these Cooper pairs can't hop around. Okay, now this is not just theory land and the solution of a particular contrived model. This is relevant physics for many strong correlation problems, perhaps the most famous one being the high TC cuprates. Okay. So
Debanjan, can I ask you a quick question? I'm sorry.
Yeah.
You may have already said this, but on the previous 2 slides, what density were you thinking about in this Hubbard model context?
So this is at some generic incommensurate density. I think in this paper they were probably looked at 0.7 or something like that.
Okay, thanks.
All right. So as I was saying, this is something that actually affects the superconducting TC in many strongly correlated systems, and one of the poster childs is in the case of whole doped cuprates. So you might have seen this kind of a cartoon phase diagram where you start out with a Mott insulator at half filling of your square lattice. Then here, because of correlation effects, you have a Mott insulator, and then you dope it with a few holes, and experimentally you find that there is a dome of superconductivity. Now, early experiments by Uemura and others, they pointed out that, in fact, the TC on this side of the phase diagram, it does scale almost linearly with the measured value of this phase ordering scale at 0 temperature. So this, I don't want to go into the details of how this phase stiffness was measured, but empirically there is a linear relationship. Okay, and then from here on, this behavior has been seen across many different systems, and so this is why anytime a new sort of strongly correlated superconductor is discovered, people often try to put it on this plot, which where you see TC versus TF, because naively, if one doesn't think too deeply about it, and this is something I'm going to come back to later, this quantity, the 0 temperature superfluid stiffness, is related to the Fermi temperature. This is definitely the case for a 2D electron gas, but this need not always be the case if you're thinking about very complicated systems. And so this was actually beautifully understood by this very classic paper by Emery and Kivelson, who argued that indeed, in the case of whole doped cuprates, you can think of 2 different energy scales. There's a phase ordering scale, and then there's an amplitude ordering scale. And TC is really determined by the minimum of both of these 2 scales. And the fact that the phase ordering scale has to sort of go to 0 as you go to half filling is simply because when you don't have any doped holes and all the electrons at half filling are frozen into your Mott insulator, you simply don't have any carriers to contribute to superconductivity. Okay. And so this is just to show that this phase ordering scale can play a very important role in the problem. So the plan for the rest of my talk is that I want to now address the question of what happens to TC in the limit of the bandwidth going to 0, not in the kinds of models that I talked about so far. Okay. And relatedly, as I go through the physics, I'm going to try and address if there are any useful bounds that we can construct on how large TC can be in principle in any given microscopic setting. Okay. So the first question is, again, as I said, what is TC in the limit of bandwidth going to 0? Now, if you think about it, there are only 2 possible answers. Either you can never have a finite TC, and given that in this limit there's only 1 energy scale in the problem, which is the scale of the interaction strength, then TC has to be related to U. Okay. Now, as you can imagine, if this were the universal answer, I wouldn't be giving this talk. So clearly the answer is TC can be proportional to the strength of attractive interactions, but then I want to address this question of how does one get that? And the reason why this is super counterintuitive is because when my electronic bandwidth, okay, for a certain band, let's say, has vanished, what that means is at the single particle level, my electrons don't have any kinetic energy, okay? So now I turn on some attractive interaction and they form Cooper pairs. But then again, the question is, how do the Cooper pairs go around hopping, okay? So what gives the finite kinetic energy to these Cooper pairs? Where is that going to get generated from? And so that is what I mean by this question, okay? So
Debanjan, can I ask, just follow up on this? So
yeah.
I guess I didn't quite understand why there's only these two possible answers. I mean, you could imagine making the situation as complex as you like, including, electron-phonon coupling, repulsive interactions, maybe some other interaction parameters beyond just a simple Coulomb repulsion. So, should I have in mind a kind of very minimalist situation for this question, where you really just have one scale and that's it?
Yes, that's the only thing I'm imagining right now, exactly. Okay. So I'm just imagining the bandwidth has collapsed and I have only one interaction scale, which is set by this attractive U, and that's it.
Okay, thanks.
Yeah. All right. And now the other question that I'm going to address during the course of this talk is if there are useful bounds on TC, okay? And there's a reason why I have useful in quotes. And so here, depending on who you ask, there are, the following options, and I'm personally inclined towards the last one, and I'll explain why I say that. And so actually, I want to start exactly with this question in a specific setting. So the reason why we are interested in this question is, suppose we have some generic Hamiltonian, which I can decompose as all of the electronic bands. This can be multi-orbital, complex. And I have some interactions, okay? And for the time being, the only assumption that I include is that this interaction is such that my external vector potential doesn't couple to it, okay? So meaning it's either, of a density type, completely local. It can be more complicated, but when I try to, introduce minimal coupling, the vector potential doesn't affect this term, okay? But of course, it does affect the non-interacting part of the Hamiltonian, okay? So how do we go about addressing that? So one possible way to do that is as follows. So imagine my system has some complicated optical conductivity. So what I'm plotting you here is the conductivity as a function of frequencies. The precise form doesn't matter. But imagine that at high temperatures, it has some functional form. That's the blue curve here. Quite often, in simple systems, that might just be the classic Drude-like form. But what we know is that once this metallic state turns into a superconductor, and for the purpose of this discussion, we can assume it's a fully gapped superconductor, there's a gap of 2 delta. This is a 2-particle response, below which there is no spectral weight. Okay, so now the total spectral weight, meaning the area under the full optical conductivity, that is conserved. Okay, so then the question is, all of this missing spectral weight, where does that go? And that actually precisely goes into a delta function at 0 frequency. And the magnitude of that delta function is precisely this phase ordering scale that I was talking about. And so in this picture, ds would be basically given by the area of this portion of the curve. Okay, so now if you want to imagine, suppose we want to ask, okay, so it seems what's the maximum value of ds that we can ever achieve? Well, imagine a situation where all of the spectral weight were to go and condense into a delta function. Okay, that is, at least theoretically, it's super rigorous and it's an extreme version of an upper bound, but it's certainly legitimate to think about what that will give us. And indeed, so this is what we're imagining at any temperature T. This is always going to be bounded from above by the total integrated weight, optical spectral weight. And indeed, this was worked out in this paper in 2019. And so if you imagine doing this, you can assume any complicated multi-orbital kinetic terms in your Hamiltonian, as long as your interaction terms have this extra caveat that the vector potential doesn't couple to it. You can calculate this quantity, okay? And okay, it has some complicated form, but it simplifies enormously in certain limits. So one of those limits is when you have maybe just one single parabolic band in your problem, and this object actually simplifies, and you conclude that TC is always going to be bounded from above by this universal object. So it's the Fermi energy divided by a factor of 8, okay? Now, usually, of course, this is also a pretty huge energy scale in the problem, but you can totally imagine going to the limit of extremely small densities, in which case this need not be a super high energy scale. So as long as this condition is satisfied, this is a rigorous bound, okay? Which is nice. But importantly, this does not mean that there will always be a bound on this quantity in general, meaning if you deviate away from this simple limit, have some complicated multi-orbital system, which is not Galilean invariant, this is not satisfied in general. Now, okay, and then there are various other limits that you can consider. Now, the question is, yes, this is a totally rigorous upper bound, but typically in most quantities that we might be interested in, this will typically lead to the conclusion that your TC is bounded by an energy scale that is of the order of a few eV, okay? So it's not a very tight bound, okay? And moreover, let's say if I wanted to apply this formalism directly to the problem of magic angle graphene, I can't do that directly, okay? And that's what I mean by this not being directly applicable to low energy bounds for various flat band systems of interest. And where this runs into trouble is that this approximation, where the interaction term does not couple to the external vector potential, is no longer the case. And I will revisit this later on. So I just want to elaborate a bit more on this point of why it's difficult to propose a very general universal bound on the ratio of KBTC divided by EF, which is what I want to do here. And so that's the question. Now, the trouble is, when we are dealing with parabolic systems, it's very nice to just write down a formula for what EF is in terms of the effective mass and the density. But the question is, how do you do that more generally? So specifically, let's say if I'm interested in flat band systems, how should I think about defining the Fermi energy, okay? Now, I guess we can come up with all kinds of definitions. I'm just going to motivate two specific definitions, which are partly inspired by experiments, because these are things that one can totally imagine doing in the lab. And so that's what's shown here in the cartoon. So imagine you're interested in some system where you have some non-interacting reference state, which is shown here on the right. So you have these different bands. These are the ones that are full. This is the one that's empty. And you park your chemical potential inside the band gap. And then you imagine filling up this band. This is just exaggerated for clarity. I want this band eventually to be a flat band. You fill it up with some electrons and you calculate this difference. Okay, so you calculate the difference between the chemical potential when you have n electrons and when you have none in this band. So this gives you some estimate for something that's like a Fermi energy. And another way of doing that is to again start out from some non-interacting reference insulating state, just as we did before, and then try to define implicitly a Fermi energy in terms of adding maybe just one extra electron into your system. Okay, so here, if you add one extra electron, you can try to extract what Fermi energy that might correspond to, given some density of states for the non-interacting system. Okay, and I'm sure you can go and construct more experimentally motivated definitions of Fermi energy. So now I want to ask the question, during the rest of this talk, when I give you specific examples of flat band models, whether or not TC over EF is actually bounded, or whether I can make this ratio arbitrarily large. Okay, so because I said that, trying to imagine a situation where a flat band system will have any finite superfluid stiffness, I want to start out with a very simple example. This is not perhaps directly relevant for twisted bilayer feed, but it at least helps us build some intuition. So I thought I might as well include it. So here's the situation I'm imagining. So my red band, which I've exaggerated here for clarity, that's my flat band. Okay, so I'm imagining taking this W120, which is separated by an energy gap from some dispersive bands, which have a very large bandwidth. Okay, and I turn on, so this is not the attractive U interaction I was writing earlier. I imagine writing down some pair hopping interaction between the flat and the dispersive band here. Okay, so I just take a pair of electrons from my red band, excite it to the yellow band, and then bring it back. Now notice this is spatially completely local, okay? And I'm assuming that this flat band is totally trivial. There is no complexity associated with it, but nevertheless, I'm interested in the possibility of this, a partially filled red band showing superconductivity. Now, in this particular regime of this particular hierarchy of energy scales, where the strength of this pair hopping interaction is much smaller than delta, which is much smaller than this very dispersive band, one can show that the phase stiffness is actually finite. It's order v squared, and intuitively, this is quite simple to understand. The only way in which the Cooper pairs that you're forming, they can hop around, is that these pairs of electrons, they undergo sort of a virtual excitation to the dispersive band. They gain the kinetic energy from this higher dispersive band, and then they come back, okay? But this is not within mean field theory, which is what we're doing here. This is not really an energy scale that affects anything because the actual transition temperature is much, much smaller. And this is something you can work out within BCS theory, okay? But nevertheless, this at least gives us some intuition for how Cooper pairs can gain kinetic energy, even if they're formed out of electronic states that are perfectly flat. Now, the other thing why this example is quite illustrative is because we can explicitly verify whether the actual transition temperature has any of these TC over EF type bounds. And in fact, okay, so I recall how I introduced two definitions, and it turns out, at least according to one of those definitions, you can violate that by an arbitrary large amount. And for the other one, you can, but again, I will show you other examples later on where you can make TC over EF arbitrarily large. So there is no fundamental bound on TC over EF. Okay. Now, again, as I said, this is not the microscopic setting that I eventually want to address, but this I think provides some nice intuitive understanding. Now, okay, so there are so far two relevant quantities that I've introduced for superconductivity. So there was the phase ordering scale and the amplitude ordering scale, and then there's the underlying Fermi energy. So one might ask if this quantity, the zero temperature value of the phase stiffness, if that actually bounds your TC. Because if you recall, when I was talking about the underdoped cuprates and this Uemura plot, empirically we find that TC does seem to scale linearly with the measured value of the zero temperature stiffness. Okay, so that's the question. And even though it sounds to be true from a very intuitive point of view, one should remember that this quantity itself does not determine TC. Okay, and so there's no reason for why this should serve as any upper bound on TC. And so the reason for that is as follows. So, well, first, I would like to argue that as a matter of principle, there is no such bound because one can cook up counterexamples where this is definitely not the case, meaning you can violate this ratio by, or rather you can make this ratio as large as you wish. Now, the reason why this often sounds like an appealing argument to make is as follows. So typically, if one is imagining TC being due to phase fluctuation effects and determined by the Kosterlitz Taulis transition temperature, it's really the phase stiffness at TC that determines the magnitude of the transition temperature. Okay, so this is what was pointed out by Nelson and Kosterlitz. And then one appeals to some hand waviness, if you wish, and physical intuition, and argues that superfluid stiffness can only be a monotonic function of temperature. So if you go down to lower and lower temperatures, this quantity is only going to increase. And so you use that to bound the maximum value of TC. But I'm not going to discuss this now, but I'm happy to come back to this later. We can construct explicit models where, in fact, the low temperature value of ds can be made arbitrarily smaller than the value of ds at TC. And we can push it to such a regime where you have some intermediate state that is a superconductor, but then the ground state is not even a superconductor. So meaning we can completely make this quantity vanish in the limit of 0 temperature. So we can't really propose bounds for TC using this as a reference energy scale. Okay, so I guess that was really my sort of preview before I start talking about the core topic of interest, which is flat band superconductivity inspired by the kinds of models that are relevant for describing the physics of, let's say, moiré materials. So actually, maybe any questions before that? All right. So from here on, when I talk about flat band superconductivity, there's something very specific that I have in mind. Okay, so what I'm imagining is a set of active bands, meaning these are the bands that I'm imagining partially filling up. So for instance, you could imagine these are the bands that everyone is excited about in TBG, which are well separated by an energy gap from all of the other bands, which are the remote bands. Okay, so, and I'm imagining that I've filled this band partially. Okay, and again, I'm only for now going to assume that I have one energy scale in the problem, which is much larger than the bandwidth of this active band, but smaller than the gap, the energy gap to these other remote bands. Okay. Now, I guess as Jason was saying, in reality, of course, there are multiple energy scales and the problem is much more complicated, et cetera, but I just want to understand this, the simplest possible problem first. Okay. Now, first of all, as I've already alluded to, it's far from being clear that if you turn on interactions, attractive interactions in this limit, that you're even going to get superconductivity. Okay, because now one has to figure out where the kinetic energy associated with the Cooper pairs are going to come from. More importantly, what we want to understand is if they're how robust is your ground state to infinitesimal perturbations. Okay, so for instance, now if I imagine turning on other interactions, what would be my ground state? Can I suppose I started out with a superconductor? Will it remain a superconductor, or will it undergo some kind of phase separation, possibly some kind of charge density wave order, et cetera, et cetera? Okay, and then finally, suppose if we do find that even in this completely non-perturbative limit, my TC is finite, what is the minimal set of ingredients we need for this flat band in order to really support a robust superconductor? Meaning, does the band need to have some special characteristics? Now, this could be some special topological property in the form of maybe a non-trivial distribution of the Berry curvature or some Chern number, or maybe it needs to have some important local geometric properties. And this is something that I want to discuss again in this non-perturbative limit. Okay. Now, the reason why I bring up topology is because topological flat bands are special. Okay, and the reason for that is that if I were to focus exclusively on these topological flat bands, even when their energy or their kinetic energy has vanished completely, they have a special property, namely that if I want to look at the Wannier functions associated with these flat bands, they're not exponentially localizable. Meaning, if I were to project my Hamiltonian just to these flat bands and forget about everything else in the problem, I can't write down a simple tight binding type models, okay, using these Wannier wave functions. So the Wannier functions have a natural, spatial extent associated with them. So that's kind of the cartoon that I'm trying to draw here. And so then one might imagine that, let's say, if you were able to somehow form Cooper pairs locally because of your attractive interaction, maybe they will have a natural tendency to get delocalized, even in this perfectly flat band limit. So the question I'm asking you here is if my stiffness can actually be, can also scale with just the the strength of the interaction, as opposed to something that we found earlier where it was set by an energy scale that really required the finite hopping. Okay, and as it turns out, I'm going to give you the answer. You can actually have something like this. Your flat bands can support a non-trivial contribution to the superfluid stiffness that scales with the strength of interactions like this, but even going beyond something like mean field theory. Okay? And yeah,
I just want to clarify something because before you were talking about this idea of getting kinetic energy via some other mechanism when you are in the flat band limit.
Yeah.
And now your point is that you can your ds can be proportional just to the interaction, and you don't need the any kinetic energy term to appear.
Exactly. So this previous sort of simple example I had was where my Cooper pairs sort of hop to the remote band and gain the kinetic energy from there. And I'm saying now I don't even need that. So in this limit where U is much smaller than delta gap. So all such high energy processes are suppressed in, let's say, powers of U squared over delta. I throw them out completely. I only focus myself on the flat band. And as I will argue actually in the very next slide, what controls this non-trivial behavior of the finite phase stiffness is that when you project your interactions, so the local attractive U-Hubbard interactions, let's say, that you started out with, to these active bands, they become kind of non-trivial. They are no longer just of the simple density type. Okay, and that is really what's going to drive all of this physics.
Thanks a lot.
Yeah, and so now, as all the students might already be starting to appreciate, in some sense, there's a lot of conceptual similarity in this problem with the famous problem of Landau levels. And that's indeed the right starting point for thinking about this problem, as I will argue for the rest of my talk. Except that at some point, I will try to come back to the question of whether the topology is really crucial or not. Okay, so now before I go into any of the non-perturbative stuff, it's always good to ask, what would have happened if I did apply BCS mean field theory in this perfectly flat band limit? And this has a long history. A lot of people have done that in the past. So in some sense, if you write down the linearized gap equations for your pairing order for this attractive U-Hubbard model, you will get back what you put in. And what I mean by that is, you solve for delta, you will find that there exists a delta, and then there is some further density dependence, which tells you that if you either empty out the band or completely fill it up, you lose superconductivity. Okay. But again, this is the pairing scale. The real question that one needs to ask is if there can be a finite stiffness. Are you just forming the local Cooper pairs, or can they actually hop around? And there was a paper, I think this is the first paper that at least I'm aware of, which really addresses this question beautifully within the realm of BCS theory. And so what they find is that at 0 temperature, the phase stiffness, now remember that in 2 dimensions, this needs to have dimensions of energy. So the energy that enters is actually precisely this superconducting gap times an object, which is related to a quantum geometric tensor. Okay, so this curly M is actually known as the Fubini's 2D metric. So if you were to imagine starting out with your block wave functions and constructing all gauge invariant observables out of it, the one that we are more familiar with is the Berry curvature, and that's the imaginary part of a more, a more general tensor whose real part is this Fubini's 2D metric. Okay. Now, and interestingly, this metric is always bounded from below by the Berry curvature. So you can even turn this result around and say that my 0 temperature superfluid stiffness is always going to be bounded from below by the same energy scale times the Chern number up to some numerical prefactors. So that is what they found. So if you were to take this literally, you would conclude that there's a lower bound on how small the phase stiffness can be at 0 temperature. Okay. So as I said, this was conceptually, in fact, this paper, and the only reason why I came to know about this paper is that in 2019, there were a number of different groups, including some of the same authors, who extended this calculation to the specific example of twisted bilayer graphene, which doesn't quite have topological bands in the sense of having a Chern number, but has something somewhat more intricate to argue that there will be a lower bound on TC. Okay. Now, this immediately raises a few questions, and this is what puzzled me, and which is why I started working on this problem. The first one is, just asking, is it legitimate to apply BCS mean field theory to this problem in the limit of a perfectly flat band? Nominally, the answer is no. But the other one is, does the concept of a lower bound even make sense? Because the first time I saw this remark, I thought somehow what was being proven is that the ground state has to be a superconductor, which we know manifestly can't be the case because insulators exist. So now if you sort of look at the fine print, what all of these papers are trying to say is that if you assume there's a superconductor and that can be described within BCS theory, it puts a lower bound on how small this quantity can be. Okay. And so we are going to go and look at that in some more detail. But I would like to point out that a lot of the physics that I'm going to show you beyond mean field theory, it's controlled by the same sort of physics that you see partly within mean field theory, even though mean field theory strictly doesn't quite work. Okay, so this was a good place to start for us. And now moving beyond mean field theory, what we want to ask is, can topological bands really support superconductivity when you turn on a finite U and have no bandwidth? And really, the question that so as I said, partly in mean field theory, you get back what you put in. But the question is, the same interactions that are apparently trying to make the system a superconductor, can they drive other competing orders? Okay, it's far from being clear that that cannot happen. And more importantly, I want to go and ask, if you go above TC, what is the nature of the metallic state out of which superconductivity might arise? And if it looks anything like the Fermi liquid metals that we're used to seeing, okay, where BCS theory, at least at weak interactions, would apply. Okay, so from here on, I am again going to try and solve certain toy problems exactly, first using Monte Carlo. So this is kind of a repeat of these calculations I showed you for the square lattice Hubbard model from many years ago, but now done for topological bands. Okay, so the setup that we have in mind is basically some kind of a lattice model for Chern bands. So +-1 Chern bands, but now I also introduce spin so that the system as a whole is time reversal symmetric. So if I have upspin forming a C=1 band, I also have a downspin forming a C=-1 band. Okay, so the problem as a whole is time reversal symmetric, and the specific choice of our model was partly inspired by a lattice model that was written many years ago, because the beauty of this model is simply by extending longer and longer range hoppings, we can play around with the bandwidth associated with these bands. Okay, so for instance, here I'm showing you how, for two different choices of a fifth neighbor hopping, you can really make your bands significantly flatter. Okay, and so what I'm going to be interested in is sort of filling up this lower band partially, turning on this attractive interaction, and then take it from there. Now, one way in which we typically characterize the flatness associated with the band is to define this ratio, which is the bandwidth divided by the gap to the other band in the system. Okay, so when I show you the data, I'm going to often refer to these two different values. So this one corresponds to a flatness ratio of 0.2, and this almost perfectly flat band corresponds to a flatness ratio of 0.01. Okay, good. So now we can put this on the computer and solve it numerically exactly. at any value of u over the bandwidth of this flat band, and also as a function of any density. Okay, so when we do that, here's what we find. Okay, so there is superconductivity. Okay, so this is great. In fact, if you calculate the phase stiffness as a function of temperature for this nearly perfectly flat band, as I said, in 2D, there's only one energy scale that we have in our problem. So in fact, it exhibits a beautiful scaling collapse. So these are all different values of u. They fall right on top of each other as a function of t over u. And so from this, if you determine what Tc is, using once again the usual BKT criterion, you find that Tc roughly scales linearly with u. So in fact, what I'm showing you here is, so this is the band that is flatter, and that almost shows perfect linear dependence between Tc and the coupling. And this one has a slightly larger bandwidth. So it's possible that the extra corrections that you're seeing, they're because of the finiteness of W over U. Okay, and you can go and study how this thing changes as you vary the filling associated with your flat band. Okay, as you either empty it out or fill it up completely, it exhibits some kind of a dome, as you would expect, because it's related to how many carriers you have put into the system. Okay, good. Now we have demonstrated superconductivity, and okay, of course, once you have superconductivity, nominally it looks like this is like mean field theory. So the question is, how do we know for sure whether or not VC's theory just works perfectly, like whether it's legitimate to just have done mean field theory on this problem? So one way to do that is to now ask, okay, what's going on with the normal state? So in these calculations, we can go above Tc, okay, and ask what's happening to the normal state out here. So the question is, does the normal state have sort of coherent, long-lived quasi-particle-like excitations, or is it some incoherent liquid of perhaps fluctuating Cooper pairs? And as you can anticipate, it's going to be this here. And the way to diagnose that, again, is to look at various other equal time correlation functions. Okay, so two specific correlation functions that we're going to look at, again, is the spin susceptibility. So if you recall, we already saw this quantity in the context of the early square lattice Hubbard model, because this tells us how the, essentially the magnetization behaves as a function of temperature. And I'm also going to look at a different susceptibility, which is the orbital susceptibility, which is a good diagnostic for measuring whether or not the system is exhibiting any diamagnetism. Okay, and so what we find is that indeed in the normal state, at temperatures significantly above Tc, the system starts forming singlets, local singlets, but they're phase incoherent, so the system can't really start exhibiting superconductivity yet. And moreover, also above Tc, the system already starts exhibiting some small diamagnetism, which is again a hint that you have these Cooper pairs, they almost want to condense, but they can't because their phase hasn't ordered yet. Okay, so if I were to use these diagnostics and sort of plot for you how the system behaves as you crank up the the ratio of u, what we find is that yes, Tc increases linearly with u, and so does the scale at which the system starts forming local singlets of Cooper pairs, which are fluctuating and starting to develop some kind of diamagnetism. Okay, and the higher up you go in your strength of interactions, the wider this regime is, where the system is sort of very incoherent. We also looked at some proxies for the spectral functions, which I'm not going to show you here. I'm happy to do that later. Basically, if you ask whether or not there is any sign of like a Fermi surface of something, then the answer is no. This looks completely incoherent in momentum space. Okay, so unlike the previous example for the square lattice Hubbard model, where this pairing scale was still proportional to u, but the phase stiffness started going as t squared over u. Here we find that these are both scaling as u, but there's this wide intermediate regime, which is metallic, but kind of bizarre. Okay, And to really understand this phase better, we can ask what about the density fluctuations. Okay, so we can now ask about how strongly is the local electronic density fluctuating in this metallic state. Okay, so to do that, we can look at the density response function, which is ultimately related to the charge compressibility, and compare it to the pairing susceptibility, meaning compare it to how the pair-pair correlation looks like equal time. Okay, and what is quite amazing is that over a very broad range of temperature scales, you find that, so this is chi inverse in units of, again, the only energy scale we have in this flat band limit. It seems they both want to go and diverge. Okay, now the pairing susceptibility diverging is good because that would hint the formation of a superconductor, but a divergence associated with the charge compressibility is weird because that tells you that the system is trying to phase separate. Okay, it means the system wants to develop very strong density fluctuations. Now, of course, at the lowest energy scales, what you find is that the inverse compressibility sort of gets rounded off, so it doesn't actually diverge, and the system does eventually settle into a superconducting state. But what we want to understand is why is this strong tendency to have both pairing fluctuations and strong density fluctuations. And the system actually becomes even more interesting when you take this limit of, so for your flat band, if you progressively make the strength of your interactions relative to the gap smaller and smaller, and look at your susceptibilities, they almost fall right on top of each other. Okay, meaning that the pair susceptibility becomes almost identical to the charge susceptibility. Okay, and then as you crank up U, they look similar, but systematically there's a deviation that develops. Okay, so the question is, it can't just be a coincidence, the near perfect degeneracy associated with the pair and charge susceptibility. So we want to ask why that is. And turns out that can be understood beautifully because there is an emergent SU2 symmetry in the problem. Okay.
Sorry, can you clarify the phrase phase separation in the context that you used?
Yeah, so basically what the system is trying to tell us is that if you look at it, so the susceptibility is almost trying to diverge as 1 over T minus TC or something like that. Meaning, if you look at the density correlation functions, it is trying to show a divergence. It doesn't eventually, this divergence is cut off at the very lowest temperature scales. But what that means is the system spontaneously wants to develop very strong inhomogeneities of different local patches of density. So it wants to sort of phase separate into different regions which have locally very different densities.
Okay, thanks.
Okay, so coming back to the origin of this degeneracy between the charge and the pair response, we can understand that by starting from this problem here. Okay, so you have, again, your local interactions, but now we want to project these interactions to this active flat band of interest. And so the way to see why the superconducting and the charge susceptibilities are related to each other, it's simplest to do the following. So imagine you were to carry out a partial particle hole transformation on your electrons, meaning you take your original upspin electron and leave it the same, but call it D, but you take your downspin electron and just rewrite it as a D down dagger. Okay. Now, what you can immediately do is if you start out, so this is basically the total electron density. This is the pair creation operator. This is the pair annihilation operator. If you were to literally rewrite this in terms of the new Ds, the density becomes like a magnetization for the Ds. The pair creation becomes like a spin flip operator for the Ds, and the pair annihilation becomes like an S minus. Okay, so that's the analogy here. And in terms of the Ds, the attractive U Hubbard model that we wrote down, it becomes a repulsive U Hubbard model for the Ds. Okay. Now there are other corrections here which can, in principle, spoil this perfect SU2 symmetry. But if you just focus on this part of the Hamiltonian, this is perfectly SU2 symmetric. And this only becomes exact in the limit where your bandwidth is 0. You take your limit of u going to 0, and the temperature is 0, and there are no further neighbor interactions. Okay, then it's literally just this Hamiltonian. Okay, and for that Hamiltonian, you can show that the corresponding BCS wave function, written now in terms of these Ds, is the exact wave function. But unfortunately, the TC of that Hamiltonian will be 0 because of Mermin-Wagner theorem. Okay, and that's because if you think about this object, okay, which basically describes the fluctuations associated with your density and pair susceptibility in the original model, this is a 3-component order parameter with a continuous symmetry. If you're in 2D, it's described effectively by a nonlinear sigma model of like this. Ignore this term for now, and the TC for that would be really 0. So there is a limit where you take the limit of u going to 0, and you can show that the ground state is a BCS superconductor without appealing to mean field theory, but the TC for that will be 0. As soon as you turn on a finite u, you will spoil this exact symmetry. And at that point, you can generate all kinds of anisotropies. So this is one anisotropy that I've written, okay, which will be set by all of these extra corrections that spoil this symmetry. And so the way to understand our results, meaning the fact that at finite u, we do get a superconducting ground state, means that the interaction at finite u, which is beyond the reach of BCS mean field theory and of these arguments, that tips the favor or the tips in balance of the superconducting ground state. Okay, and so there, once you have derived an action of this type, you can calculate TC. TC will be given by this the strength of attractive interactions times this object. Notice that when J_perp goes to 0, which is the limit of the perfectly symmetric SU2 invariant point, this again vanishes. Okay, and we can literally do an experiment, a numerical experiment that tests how fragile your system might be to this SU2 symmetry. And one way to do that is to just turn on a very small nearest neighbor attractive interaction. Okay, so here I'm turning on an attractive interaction, which is 10% of your U. And immediately you find that, in fact, the system wants to go and phase separate instead of becoming a superconductor. So the red curve is the inverse charge compressibility, which goes to 0, meaning the charge compressibility diverges. And so this is the point at which the system becomes phase separated instead of being a superconductor. Okay, so again, this is something beyond the reach of BCS mean field theory. So if I were to summarize the lesson that we have learned by doing these sort of exact calculations, they're as follows. So at this non-perturbative limit, you have an incoherent metallic normal state that can give rise to a superconducting ground state in principle. It need not always give you a superconducting ground state, unlike what just a simple application of mean field theory would predict. And this normal state is pretty anomalous because it has strongly fluctuating density and pairing correlations for at least this specific problem. But in fact, this is quite reminiscent of a Pomeranchuk type effect. Okay, and by that I mean, so the ground state, okay, is either a superconductor or possibly some other kind of ordered state which has very low entropy. But when you heat it up, you go into this region which has lots of strong fluctuations. These fluctuations effectively are described by the fluctuations of this order parameter n that I had introduced. Okay, and the reason why I find that interesting, because this is quite analogous to, in spirit, to the Pomeranchuk effect that a lot of different groups have observed in TBG and in other moiré materials, where you heat up the system and suddenly it gains a lot of entropy from something that starts like looking like local moment type fluctuation, but in a metallic state, which is exactly what this thing is as well. Okay, and from a more conceptual point of view, this approximate SU2 invariant limit is a good starting point to think about the physics in the regime where U plays a fundamentally non-perturbative role. And the reason why all of this works out is because once you have projected your local interactions to these non-trivial flat bands, the interaction now does couple to an external vector potential because it's no longer just a simple density-density interaction. In fact, even though your single particle band has no kinetic energy and no current associated with it any longer, the non-trivial block functions actually lead to a finite current whose scale is set by the interaction. So this is purely an interaction-induced effect. Okay. So this is all good, but now in the last few minutes, I want to ask the question of if topology is essential, meaning so here we started out with a problem that actually looks a lot like Landau levels. So the problem was fundamentally, 2 copies of a Landau level for spin up and spin down electrons, and you turn on some attractive interactions. Now these could be because of some electron phonon interactions or something else. But the question is the topology really important? Meaning, do the bands need to have either a Chern number, or at least you might ask, do they need to have some non-trivial distribution of Berry curvature, which perhaps averages to 0, but nevertheless, having this finite is important somehow. And finally, is there a solvable limit? And by that, I mean somewhere perhaps where we can do some analytical work, even though this is non-perturbative, which can help us understand the interplay of superconductivity and all the other competing orders that are relevant. And so this is something that we've been working on recently. And surprisingly, or actually now in hindsight, perhaps not so surprisingly, the answer to this question is yes. So yeah, we can, realize all of this physics in completely trivial flat bands. Moreover, we do not need, any non-trivial distribution of Berry curvature. In fact, in the models that we study, that I'm going to talk about in a second, the Berry curvature is identically 0 everywhere in momentum space. Okay, so it's not just that it's not a Chern band, the Berry curvature just vanishes. And yet we can basically repeat everything that we have seen in these topological bands. And finally, in the same class of models, there is a solvable limit where we can gain some analytical understanding explicitly, starting from a particular limit. Okay, so here is the example of the Hamiltonian we're considering. So we have, again, 2 pieces. There's a kinetic part of the Hamiltonian, which depends on a parameter zeta. And so we engineer this Hamiltonian to yield isolated flat bands with a vanishing Berry curvature, okay? Now, zeta, you might ask what zeta is. So zeta actually controls the spatial extent of the one-year functions, okay? So again, one important thing to remember is that the band is topologically trivial, so I can construct exponentially localized one-year functions, but I can imagine tuning the minimal spatial extent associated with these one-year functions. And there's nothing wrong about having a finite spatial extent, meaning a finite Fubini's 2D metric, even when the Berry curvature just identically vanishes, okay? And the good thing is that if you take this limit of zeta going to 0, that represents a completely decoupled problem, where basically the lattice falls apart and you just have a bunch of decoupled sites, okay? So the interaction is again going to be the same because I want to compare my analytical understanding again with these Monte Carlo calculations. So there's some local attractive U Hubbard type interaction that favors the formation of singlets, spin singlets, and then you have some nearest neighbor interaction, and we can tune the sign of this to be either attractive or repulsive, okay? So just to show you the explicit form of this Hamiltonian, that's of this type. And so this zeta helps control the extent of the one-year function, basically not by tuning the energetics, but by tuning the form of the block functions, okay? Now, why is this interesting? Because now I can imagine doing some kind of perturbation theory in a small zeta, okay? So basically, as I said, in the limit where zeta is 0, I have a bunch of decoupled sites. I can solve that problem. This leads to a hugely degenerate manifold. And then I can do degenerate perturbation theory in a small zeta. And what that gives me is some effective model that looks like an XXZ model, again, just like what I was discussing earlier in the context of the SU2 symmetry. And then there are a whole bunch of other complicated terms that I don't want to go into here for now. And the right is, this is just a visualization. So these different colored disks that you see, this is really just showing the amplitude and the phase of the exponentially localized one-year functions that you can construct. And then these arrows, they basically denote the leading processes, so to speak, in powers of zeta for all the different terms that you generate, okay? So when you switch off V completely and again, take the limit of u small so that the other terms here can be sort of ignored. This goes back to a perfectly symmetric Heisenberg model. That's the SU2 symmetric limit that I told you about earlier. That still works out to be the case here for these flat bands. And so in that limit, TC would be 0. But the moment you turn on, all of the other perturbations, which actually are controlled by a finite u and so on and so forth, you can basically, tune the system to be in a multiplicity of ground states. And again, we can repeat these Monte Carlo calculations. So I'm going to be brief here because so what we find is TC. Okay, actually, this is important. So the important thing is J-perp is what really sets the scale for the superfluid stiffness. And here you can explicitly see that that scale is set by zeta squared times u. Okay, and so in fact, if you look at the transition temperature for superconductivity as a function of u, it does exhibit this zeta squared times u behavior. But again, the normal state is weird. It is like this incoherent liquid of Cooper pairs that shows a suppression in susceptibility. It also shows this tendency to have a diverging compressibility, which just gets rounded off at the last moment, and when the system becomes superconductor. And the other thing I thought I should mention is that even for this model, you can explicitly go and calculate, these different definitions of the Fermi energy that I'd introduced. And turns out for this model, in this perfectly flat band limit, you can, violate this bound by an arbitrary amount. So just goes on to show that, there's no fundamental bound on TC over EF in general, as soon as you step away from nice parabolic bands. Okay, now the really cool thing about this model is that you can tune it into all kinds of other competing states, which includes, by turning on a very, very small nearest neighbor repulsion, you can tune it to be a charge density wave in this perfectly flat band limit, and most interestingly, a super solid. Okay, so super solid is a phase of matter which is both crystal, which has some kind of spontaneous breaking of translational symmetry of the underlying lattice, and it's simultaneously also a superconductor. Okay, and I'm not aware of any other electronic models in the past where one can reliably show that you can get a super solid ground state, but that almost comes here for free. And I can discuss more details of this if someone's interested. Okay, so with that, I would like to conclude with an outlook. So hopefully I've been able to at least convince you that the question of flat band superconductivity is pretty non-trivial, even if you assume that there is some microscopic attraction that's already present, because you have to grapple with these very important conceptual issues of, even if you were to form Cooper pairs, how are they actually going to contribute to finite supercurrent, which is, really the defining feature of superconductivity. If you want to go beyond mean field theory, of course, if you do mean field theory, you will find that, yes, you can get a superconductor. And so now with the technology that we have developed, of course, we want to apply this to MA TBG, and well, yeah, all I'll say is just stay tuned for that. And from a more sort of theoretical perspective, I think we still need to understand, given certain classes of models, even including those that are relevant for flat band physics, can one really come up with a precise formulation of a low energy bound, meaning write down bounds on TC over U, let's say, or TC over something else, almost at the level of a theorem. So one of the theoretical bounds I discussed early on is of that type, where you bound it by the total spectral weight. But typically, in a lot of the problems that we would be interested in, this is not a very tight bound. So can we have a more low energy bound along those lines? And there's been some recent progress on that as well. Okay, so with that, I'd like to thank you for your attention and take more questions.